Our next plenary speaker is a local hero, so to say, Sergio Idelsohn. He spent his academic childhood in Argentina, in Rosario. He did his PhD with a very famous person from computational mechanics from the early days, Professor de Voybeek in Liège. And he's now at Cimne, and he's one of the main players in the field of treading on the cable of the Particle Finite Element Method. And today we're hearing something about the second generation of particle finite elements, and I'm already eager to hear about it. So please, Sergio.
Okay, thank you very much, Mr. Chairman, for the presentation. Thank you also the organizers to invite me for this plenary lecture. And I would like to thank also my co-author, Eugenio Iñato, that we know very well, Norberto Nigro, Ricardo Rossi, Julio Marti, Pablo Becker, and Juan Jimenez. In particular, Norberto Nigro and Juan Jimenez from Santa Fe, Argentina. We are working in this particle method after several years. I will start just with a very fast explanation of what we call the Particle Finite Element Method second generation in a graphic way. Suppose that we have a mesh, a fixed mesh, and suppose that we have some particles inside. And suppose also that from the previous time step, we know the velocity, the acceleration in each particle, and also we know the velocity and the acceleration in the node of the mesh. Then, at the first step, we move the particle. We move the particle integrating the velocity. How can we do this? Because we know the velocity in each point here. Because we know the velocity on the node, we can interpolate, and we know the velocity in all the intermediate position. Then we can very well integrate the velocity in the previous step, in the time n, to obtain the new position. In the same time, during this integration, we can also integrate the acceleration, because we know the acceleration of the node, and for this reason we know the acceleration in all these points. Then, this is an explicit step, because all the information that we have from the previous time step, and we can do this for each particle independent of the other. Then we can integrate this streamline, and we can integrate this acceleration around this streamline using the information that we have from the previous time step. Suppose that we do this for all the particles. These are the new position of the particle, in which they have a new velocity that we call v hat. It's not the final velocity. It's an explicit velocity that I evaluate integrating the acceleration of the previous time step. When we have moved all the particles, I can project this velocity and pressure on the node of the mesh. For this, I use all the particles around each node. I can use some particle or all the particles, and I can use any projection method. I can use a weighting projection method. I can use the shape function to project. One method to project, of course, we have a projection error during this step. Then, at the end of the day, I will have the velocity in all the node of the mesh. I will have the velocity, the new velocity at all the node of the mesh. This is that we call v hat at the x position. Then we solve the standard Navier-Stokes equation. We solve the standard Navier-Stokes equation, in which we introduce also the incompressibility condition while using an incompressible fluid. Because during this step, perhaps these new velocities are not incompressible. Then we solve here the standard Navier-Stokes equation without the convective term, because we have yet convect all the particle. Then at the end, we have the increase of the velocity in all the nodes of the fixed mesh. In all the nodes I will have. And then I can interpolate from the node to the particle. Then at the end, I will have Vn plus 1 in all the particles. And I continue the process. This is the idea of that we call PFEM second generation. This is the idea. And we can find, you can find more explanation in this publication of 2 years ago. Then, in fact, the PFEM second generation is exactly the same as the standard finite element method, without the convective term, because at the end we solve for the mesh the Navier-Stokes equation with the compressibility equation without the convective term. We solve this equation at each time step. Then the question may be, why avoid the convective term? Why? In fact, we are not avoiding the convective term. We are evaluating the convective term in a different manner, moving the particle and projecting instead to use the standard convective equation. Well, look at this example. Here we are solving a pure convective problem. This is the Sale-Sack disk. We are using a coarse mesh, 100-100, and we are solving this problem using a Courant number equal to 5. This means it's a very large Courant number. We are moving each particle 5 elements at each time step. Here we are using PFEM2, and here we are using a standard formulation with finite element using an Eulerian formulation. You can see that if we use Courant equal 5, we have a very bad solution after 1 or 2 tours of the circle. We don't have any more nothing. And we need a very small time step, Courant 0.5, to have enough solution. This means using this method, this is a very convective problem, we can use a time step 10 times larger than in the Eulerian formulation. Look at this other example. This is the Rayleigh-Turner instability. We have here 2 fluids. One is more heavy, and we have here the gravity. And we are solving this problem using a delta t, a small delta t, 10, a delta t equal 25, a delta t equal 100, and a delta t equal 250. If you look at the result, all the results are nearly the same. It's not exactly the same, but are acceptably the same. This means that to solve this problem, you can solve this problem using this large time step. Remember that it's large compared with this, but it's very small, the time step. It's 10 minus 4 by this. Okay, but in solving this problem, we need, in the same computer, 1 hour and a half, and to solve this problem with this delta t, which nearly the same result, we need only 3 minutes. Then, of course, we will use this solution. What happens if we try to do this using a standard finite element method, using an Eulerian formulation? We can solve this problem only with a small delta t. This means that we need more than 1 hour to solve this problem using the standard finite element method. Using the particle finite element second generation, we need only 3 minutes. This is why we are trying to avoid this convective term. Excuse me. Okay, let's go to this equation. This is the standard Navier-Stokes equation written in an Eulerian frame. This is the standard. We have here the partial derivative of the velocity. These are the convective terms, which are we're talking now. And this is the viscous force, the pressure gradient, and the gravity force. X are fixed, and V the X is. In the Lagrangian formulation, in the Lagrangian frame, we have the same equation without the convective term, but we need to add this equation to evaluate the particle position. Then, to solve this or to solve this is exactly the same in the continuous, not in the discrete. And now the unknown are the velocity and the position of the particle. This part is that we have called the acceleration. The force divided by the density are the acceleration. Both acceleration are nearly the same. One are for fixed x, the other are for moving x. But this has this convective term here, and this don't have the convective term. Then, suppose that we need to integrate this in time. We must go to Vn plus n to Vn plus 1 by integrating the acceleration plus the convective term. If we are using a theta method, we will evaluate this and n plus theta by delta t. And suppose if we are using Kramnik-Nixon, we will use theta equal half with the definition of this. And the Lagrange method is exactly the same. We integrate the acceleration, we don't have this convective term, and we evaluate the acceleration in n plus theta, and we need also to integrate the velocity to have the new position. Suppose you use exactly the same formula using some approximation of n plus theta defined by the function and n plus the function and n plus 1. Which is interesting to say that using the Lagrangian formulation, we have other possibility with the same theta idea. Suppose this is the classical, this is the standard that I explained before, the acceleration in n plus the acceleration in n plus 1 by a theta. We can use a half or another theta. Normally we use theta equal and half. But here we have other possibilities. This is, we can integrate the acceleration in time n and integrate the acceleration in n plus 1 using a moving x. Look at the difference. Here we have a fixed x in the standard method, and here we have a moving x, a moving particle in this new application. Of course, this is very easy to evaluate because this is explicit, but this is not so easy because it's implicit. Then we can mix. We can use this for the explicit part and this for the implicit part. And we have this that we have called in a paper Chiva's integration plus implicit correction. That is the integration that we are going to use. And exactly the same for the integration of the velocity to evaluate the particle position. We have the standard integration, we have the new integration, and we have the mixed integration. Look at, this is, as I say, explicit, this is implicit, this is explicit, and this is implicit. Then, I will repeat again, now that we know the equation, I will repeat again the graphical idea of the PFM. We have the velocity, the acceleration in all. In the particle are also in the node. We integrate the velocity using the velocity at the node in time step n. We integrate the acceleration to go to the new position. We have all the v hat in the particle. We project using some projection. We solve the standard Navier-Stokes equation to evaluate the increase of the velocity. We have the increase of the velocity on the node, and we interpolate to the particle. This is the idea that I repeat again. Okay, some implementation when we have multifluid, when we have two fluids. Of course, this is the problem of all the methods that use fixed mesh. If we have two fluids and the interface between the two fluids is going through one element, we need to do something to improve the solution. Suppose that this is the position of the particle after moving the particle. We have the red particle, we have the blue particle. It's not easy to have a very fine definition of the interface. Here we can say that the interface is something very complicated like this. We are not using this. We approximate the interface, but some linear between the blue particles and the red particle, using some approximation using the distance between the interface and the particle. In this case, this particle, for instance, that is red, in this moment will be considered as blue, and this particle that's blue will be considered as red. But it is important to say that the particle conserve all the time the physical characteristics. Then this particle that now we will consider that blue will move, and perhaps in the future will be. He remembered that he is a red and will become a red. Then this is the Lagrangian evaluation of the interface position. We are not doing a level set moving. We are evaluating the interface by the Lagrangian way. And in order to improve the approximation, we add some enrichment space here. This is, for instance, the approximation of the velocity. These are the standard shape function used in finite element. And we add some enrichment function that I will show now. This is some of the enrichment that we add when we need to have a jump in the gradient of the unknown. This was proposed by Coppola, Owen, and Codina in 2005. Or we add some discontinuous function when we need to introduce a discontinuity of the function or the unknown function itself. Let's go to the error analysis, which is the most important part. I will move directly to the conclusion of the error. We have analyzed the error that we made using an Eulerian formulation and a Lagrangian formulation. This all was explained in this publication of this year. But the conclusion is the following. This is the error that we can find when we use a standard Eulerian formulation. H is the size of the mesh, capital H, and we have here this represents the second derivative in space of this function, and this is the second derivative in time of this function. And this is the Lagrangian error that we obtain. If we compare these two equations, we will see that there is an error due to the viscous term, the diffuse part of the equation. And you will see this is nearly the same in both approximations. The diffuse part of the Eulerian, the error in the Eulerian approximation is nearly the same of the error in the Lagrange approximation. But if we look at the convective part, this is the error in the convective part of the Eulerian formulation, and this is the error in the convective part of the Lagrangian one, in which we have added the projection error proportional to small h, where small h are the distance between particles. Then, it is important to compare these two kinds of error, and I will show just this conclusion. This is the main error in the Lagrangian, and this is the main error in the Eulerian. And if we compare these two equations, we will see that the only difference is that this parenthesis that here is this, in the other is here. Then the second derivative in space and the second derivative in time, in the Eulerian is also for the gradient of the velocity, and in the Lagrangian, the gradient of the velocity is outside. This is a small difference, but sometimes it's a big difference. For instance, this is the Lagrangian error for the time, and this is the Eulerian error for time. And if we develop this, by dividing this in two parts, we see that this Lagrangian part is only this first term here. The other term, for instance, this is the second derivative in time of the gradient, is not included here. What does it mean? That if this term is very big, I will have a big error in an Eulerian formulation. If this term is small, I will have small error. This is the normal conclusion. Then Eulerian error are bigger than Lagrangian error when the variation in time of the gradient of the velocity are bigger. And this is the other case. Concerning the projection error, I would say that, well, some people say, well, you have many projection errors because you need to project all the time on a fixed mesh. Well, I would say that the projection error is involved in all the methods that use a fixed mesh. in Eulerian and in Lagrangian, because if you need to represent a function that moves in a fixed mesh, you need to project all the time this shape on the fixed mesh. For instance, suppose that you have a very simple problem. This is a one-dimensional problem. Suppose that you have a velocity in this direction, and suppose that you need to convect a function. For instance, the temperature. You need to convect. You just move. They are not diffusion. You are just moving this function. Okay. If you are using an Eulerian formulation, you have the first step. This is the first time step. You have this new position of the time. But you have this fixed mesh. Then the only way to represent this function on this fixed mesh is this solution. And at the next time step, you will to convect this solution to the new step, and you have a fixed mesh, then we have this. Then at the end of the day, in two time steps, from this shape, you have this shape. And this is an Eulerian, this is a standard formulation. Then, why? Because, as I showed before, the error in the convective term of the Eulerian formulation is proportional to the variation in time and space of the gradient of the temperature. Here, the gradient in one step goes from 1 to 0. Then a big gradient variation, then you have a big error. What happened in PFM2? What happened in Lagrangian formulation? Well, we have the same situation, but we move the point, and we preserve the temperature or the unknown on the particle. We project on the fixed mesh only to evaluation of the diffuse part, only for the evaluation of the conductivity, only for evaluation of the viscous term, but not for the convective term. Then, if we have a problem in which they are not diffusion, at the end of the day, we have this. Then the error here is proportional to small h and not to the gradient of the variation of the gradient of the temperature. Then, as a conclusion of this part, we can say that we have error in Lagrangian and we have error in Eulerian. In the Eulerian formulation, we have error in the integration of the convective term and error in the integration of the diffuse term. In the Lagrangian formulation, we just have error in the evaluation of the diffuse term, and we don't have error in the evaluation of the convective term. For this reason, when we have a problem where the convection is dominant, we have good result using the Lagrangian formulation. I will show you some examples. This is a manufactured example. This is a fluid which is turning at different velocity. These are the particles turning. And we put some source to hit this. In other way, in order to have this final solution. I repeat, this is a manufactured. We know the analytical exact solution to this problem. Then the temperature is going up and down, and the fluid is turning here. This is the idea of this example. I will show you some result of the error. This is using two different time steps, with a small time step and a big time step. Look at this is after some time. This is the error using a large time step using the Eulerian formulation, and this is the error using the same time step using the Lagrangian formulation. Of course, using a small time step, you also have good result in the Eulerian formulation. But here, you see that we have the same error using a time step 6 compared with a time step 0.6 for the Eulerian formulation. Then 10 times larger. The same happened with the size. Here we are solving the same problem using 2h, h, and h under 2. This is the result using Euler with 2h. This is the result using Lagrange with 2h. This is the error. And we see we have, again, the same idea. If we compare the variation of the error, the convergence of the error, we see that for very small time step, we have better conversion in the Eulerian formulation than in Lagrange one. We have better formulation. But when we see for large time step, we have exactly the same conversions, but with a better factor. And this is very important because we have the same error here with a mesh which is exactly the double than the other. This means that we can have, for this example, exactly the same error using a mesh which is just the double. This is in one dimension, the double in time. In two dimensions is 4 times better, and in 3 dimensions is 8 times better. This means, for this in particular problem, we can solve this, for this time is in 2D, 4 times faster. And remember that the time was 10 fast started. At the end of the day, we can say that to solve this problem, which is very Eulerian problem, and we are not moving interface here, you cannot say that this is very Lagrangian problem. This is very particular problem using an Euler. You can solve this problem 40 times faster with exactly the same error. And if we are in 3D, 80 times faster, with exactly the same error. Finish in 4 minutes. It's okay? Okay, look at this example. This is a simulation of the brake of a liquid jet. This is for the diesel engine. This is the gas oil going inside the cylinder. We are using here a very fine mesh and a very small time step to reproduce this problem, delta t 10 minus a. But in any case, you will see that using the Lagrangian formulation, we are using a time step 5 times larger than those using an Eulerian. If we use the time step 50 by 10 minus 8, we have a good solution. If we try to use this time step using an Eulerian formulation, in particular, we are using here the open form code, does not converge at all. In one case, we have the result in 1 hour. In the other case, we have the result in 11 hours. This is a big difference in the practice to have the result in 1 hour and to have the same result in 11 hours. This is another interesting idea. This is the classical dam brake problem in which there is an obstacle. We are solving this problem using 2 fluids, the water and the air, because it is very important here to solve also the air, because there is a bubble here. You see there is a bubble that break, and then to represent very well the air is very important. This was solved experimental by Koshizuka. Thank you very much, Professor Koshizuka, that is here. He solved experimental, and you see that the results are in a good agreement with experiment. But I would like to show you this. Okay, we are solving this in 3 minutes, which have a good result. But we can also solve this problem in 31 seconds, just increasing the time step. Or we can solve this in 5 seconds or in 2 seconds. Okay, you will say, well, this is not very good result, but this is a result. We can have, yes, if you try to solve this using a Eulerian formulation, it does not converge using this large time step. And this is one of the particularities of this method, that you can increase and increase the time step. You don't have a very accurate resolution, but you have a solution. And this is because the error is big, but not so big as the error that you have using an Eulerian formulation. Okay, this is fluid structure interaction. This is the Tarek benchmark. And we, well, it's very no problem in which just we are solving this. I will show some examples to show that we can solve many problems using this PFM second generation. We are using here delta t of this order. I'm sorry. 10 minus 2. Normally this is 10 times larger than the standard that you find in the literature. We can solve this problem very fast. Remember that we are solving this problem using a fixed mesh and particle. This is the elastic part. This is this part. I represent in this. You can see the fixed mesh used, and you can see here the particles as they move. We are moving all this problem. This is more expensive to solve a standard problem, but as we are using a delta T 10 times larger than the other, we have a better and more efficient result. Well, this is the Rayleigh-Taylor stability in 3D. We're using this time state, which is also very large. You can test this example with this delta T. We cannot solve this problem using an Eulerian formulation with this delta T. This is a mold filling. You see, another particularity of the Lagrangian formulation is that you see the fluid is very liquid. They are not, in the Lagrangian formulation, they are not artificial diffusion. They are not introducing viscous diffusion. You see this is very, very liquid. It's the true viscosity that we have. It's not easy to find. And here we are also solving this using large time step. This is a problem of oil and water. We are pushing water to push the oil, the petrol, to go out. And we see here that once the water, what we see here is the water, and the black is the interface between the water and the petrol. Once the water finds the other side, there is a flux in this way, and the petrol remains in the other way. This is an example of combustion. I finish in 2 minutes. This is an example of combustion with melting, dripping of a candle. We are burning a candle. You see here there is a temperature profile. The viscosity here of the fluid is dependent of the temperature. Then, after some heat, the fluid become more fluid and melt and drip. And this is the fixed mesh that we are using. You see that we are using a more fine mesh near the part of the candle. And this is the polymer part, and this is the mesh that we are using. And this is another example just to show that the possibility. This is a landslide and debris flow. We see here we have a rigid body moving a fluid and a solid part. And we are solving this problem using a moving mesh. Because remember that in one moment we have all the information on the particles, and we need to project this information to the mesh. In this moment, we can move the mesh and put the mesh in another part without any error, because we don't have information. We have, in this moment, all the information on the particle. Then we can put the mesh in another part and project in the new mesh and not in the old. And this is a catamaran sailing over here. Also, we are solving all the problem. We are solving the water and the air, and we are just moving the mesh for represent the movement of the catamaran. Okay, I finish. My conclusion is for convective dominant problem, the treatment of convective term, this is for diffusion and this is for the Navier-Stokes, may be avoided using this moving of the particle and projecting. In the majority of the case, it's more efficient. I say in the majority of the case because in some times it's better to use an Eulerian formulation. For instance, if you have a nearly stationary problem, the gradient of the velocity doesn't change, and of course it's better to use an Eulerian formulation. To move particle is inexpensive. It's inexpensive because we can move each particle in parallel. We can evaluate the movement of the particle independent of the other. Then we can do this in many different processors. The efficiency of moving particle and projecting a efficient mesh is based on the possibility of perform large sum step. If we cannot perform large sum step, better use an Eulerian formulation. And this happens when this is smaller than this. And when we have multifluid with internal interface, this PFEM2 is much better because we don't need to solve the level set equation, which is very convective equation. We convect, we move the interface, moving the particle. We don't need to solve this equation. Thank you very much for your attention. I'm sorry to be late.